Okay, it's 9 a.m. So we can continue, right? So let's look at this problem. Basically, there wouldn't be any introduction because all major points that we need to know to solve problems from this recitation class we discussed in the previous lecture and previous recitation class. So as a result, I will just dive into the problems. So the first one. Let's assume that we have an infinitely large charged surface, plane, right? Okay, there's something in the chat. Right. Okay, attendance code. Again, I just answered a few minutes ago. I only check attendance, lecture attendance. I don't check attendance in the recitation classes. Okay, so back to the problem. So we have infinitely large charged surface, right? And it's negatively charged, right? So then, and surface charge density is given. Then what if we take a proton, charged particle, and position it here? First, let's just discuss conceptually what will happen, and then only start solving problem. So, and the proton is shot with this initial velocity that way, right? Of course, what will happen? A negatively charged object, positively charged, of course, they will be attracted. And as a result, this proton will move decelerating, right? So slowing down, and eventually, sooner or later, it will stop for a moment, turns around, and start moving in the opposite direction. Pretty much what we need to find, we need to find this distance before its turning point. All right? Okay, so that's the problem. Now let me write what else is given, and then we will actually start solving. Again, guys, if something is not clear or I said something and you didn't understand, okay, tell me immediately. So what else is given? Velocity I wrote. All right, probably let me draw a picture. And then I will start adding missing parameters because without picture, I cannot do that, right? All right, so first, let me draw, I need probably first show the proton. So here is the proton, charge Q. And of course, first it travels with initial velocity V0, which is given, right? And then, of course, it will move this way, decelerating, and then sooner or later it will stop and start traveling in the opposite direction, right? Now, since we're going to basically deal with one-dimensional vectors, let's introduce coordinate system. Without coordinate system, this problem will be impossible to solve. Okay, so let me introduce coordinate system. All right, so this is my x-axis. Let me position origin over here. And basically what we need to find, it's this, okay, let me call it x still, but it's a particular x. So that's what we need to find. All right, and so now I can add additional parameters. So first of all, initial position of the proton, since I position my origin over here, so initial position of the proton is 0. Right, so I can write, so x0 is 0. Then, what can you tell about this point, turning point? Because that's our final point. It's a turning point, and from physics 1, you remember what happens with the velocity at the turning point. Velocity is 0. Of course, velocity changes its sign, but at this problem, it doesn't give us a significant amount of information. What we need to remember that final velocity is 0. So I can write that v equals 0. Basically, at this point, I can show that over here, v equals to 0. So there's two pieces of information. And now let's also show electric field lines, because this negatively charged plate, of course, creates an electric field lines. we are still slightly ahead of the lecture. So tomorrow I will sort of derive the expression for the electric field created by an infinitely large surface. So right now we will just use the formula which we will derive tomorrow. And also this surface creates what is called a uniform electric field. Uniform electric field, right? So uniform, it means that electric density of electric field lines must be exactly the same at any point. So let me draw a few electric field lines, right? So maybe one over here, one over there, here, right here. And since it is negatively charged, you remember electric field lines, they start on positive charges and end on negative charges. Since we have a negatively charged surface, of course, electric field lines all end on the surface. And of course, on this side of this plate, I can draw these electric field lines. Okay, so that's my E. Okay, now I think my picture is more or less complete, right? I don't think that I need anything else, except for I need to write down what needs to be found. Find X, right, final. Okay, so now the whole picture is here. Now, let's discuss the structure of the solution. It's very important to see the structure because then you can apply that structure to solve similar problems, which are slightly different, right? And sort of like let's create a skeleton of the solution. And let's start from the very end, from what needs to be found. Okay, I will probably show it at the bottom below this. So at the end, we need to find X. That's our final point. In the solution, final point, right? And X from physics 1, it's one of the kinematic parameters. You remember in physics 1, you had three levels of kinematic parameters. The top one, position, distance, displacement, right? You remember? Then, and this actually from that level. Then if you differentiate those parameters, you can get to the velocity level. Velocity, speed, instantaneous, average, and so on. So velocity level. And then the deepest level, if you differentiate one more time, you will get to the acceleration level. All right? So these three levels, and position is from the top one, from the position. So now, what do we need to know in the previous step in order to find position? You remember, we usually use, you usually used in physics 1 kinematic equations, right? In order to find any of those kinematic parameters, kinematic equations. And the major part of those kinematic equations is an acceleration. Every time, first you would find acceleration, and then you, using kinematic equations, you would find either position or travel time or velocity, right? It's coming back from physics 1. So as a result, the previous point which we will have to find acceleration, right? So acceleration, and of course, equations connecting these two points are kinematic equations. Kinematic equations, right? So again, that's basically the final part of the problem. So now let's move forward, right? Now, in order to find acceleration, what do we need to know? Newton's second law. We need to know force. Force acting on a particle, in this case, proton. So electric force, that's the point before that. And of course, here, Newton's second law can be used. Okay, I should have used blue, but okay, I forgot. So that's the bridge which will allow us to move from here to there. And so the first step, so what do we need to know in order to find electric force? In the previous lecture, we introduced that formula, and I told you it's one of the fundamental formulas in physics and in EMAG, expression for the electric force, right? QE. So in order to find electric force, we need to know the electric field. So the first step, electric field, and then in order to find the force, we can use this formula F equals QE. Basically, that's the skeleton of the solution. That's the solution for this problem. So everything is here. Now we just need to take one step at a time and reveal all that solution in details. And these are bridges. So we need to use first this formula, then this, and then one of those kinematic equations. Right? So now let's start with the electric field. Right, electric field. And I'm going to use the vector form. Of course, this vector is one-dimensional, right? So it's not that complicated, but you will see why. But you will see in a second why I want to use the vector form. So again, tomorrow only we will derive the formula for the electric field created by this charged surface. So right now I will just write down the expression. So expression for the electric field, maybe I will write here, it's a magnitude. It's a surface charge density divided by 2 epsilon naught. Tomorrow we will derive it. Right? So now it's a magnitude, but I want to write in the vector form. I want to write in the vector form. So I will write, first of all, our surface charge density is negative. I want to use absolute value, and I will show the minus explicitly. You will see in a second where. So I will put an absolute value of eta. Then, of course, divided by 2 times epsilon naught. And now direction. Electric field we drew. You see, it points that way. Right, you see. And that is the negative x direction. So if I want to write in a vector form, I have to, of course, show the direction as minus I hat. I hat unit vector in the x direction. Right. So basically, this minus appeared over there. I just wrote in this way. Right. Okay, so that's the expression for the electric field in a vector form created by this surface. Okay, so we are here. Now, using this formula, we can get expression for the electric force acting on the proton. Right, so, and this is the charge of the proton. So now the second step, F electric equals, of course, QE. And so now we just need to rewrite this and multiply it by Q. So it will be Q times absolute value of the, it's a Greek letter eta. You remember in the previous lecture we discussed linear charge density, surface charge density, volume. This is a surface charge density. Right. So, and divided by 2 times epsilon naught, and still, of course, in the negative x direction. And of course, it makes sense because we just discussed conceptually, right? So that this proton is going to be attracted by this negatively charged surface. So the force will be that way in the negative x direction. And we're getting negative x direction of the force. Right. Okay, so now we are at this point. Now we need to use Newton's second law to get information about the acceleration. Okay, so now the next one, acceleration, and I will use the vector form. F divided by m, so Newton's second law. So we just need to take this and divide it by m, that's it. We just keep adding constants to the expression, right? And so it will be q times absolute value of eta divided by 2m epsilon naught, and in the negative x direction. And again, negative acceleration makes complete sense. It's just, again, negative acceleration. Minus means that acceleration is that way. So, of course, proton travels this way in the positive x direction, but of course it's slowing down, decelerating. It means acceleration that way. Again, we knew it conceptually from the very beginning, and now we're getting it mathematically. Right. Okay, so now we are at this point, so acceleration. So now, next step. Can we use, now of course we've come to this point, and we need to, of course, discuss kinematic equations. But the first question, can we use kinematic equations? what should we check first before we can legitimately start using kinematic equations? Again, physics 1. Kinematic equations can be used only if acceleration is constant. Only if acceleration is constant, only then you can use kinematic equations. Let's check. Constant, 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 constant. Acceleration is constant, so yeah, we can use kinematic equations. Right? Okay, let me write down. So it's a constant. So we can use kinematic equations. Again, if acceleration is not constant, it would be, okay, illegal, right, to use kinematic equations, right? Mathematical crime, a physical crime, right? Right. So now, of course, now the question, which kinematic equations can be used, right? So there are several of them, right? I'm thinking, should I write them down quickly or not? Okay, maybe let me refresh quickly. All right, x equals x naught plus v naught t plus 1 over 2 at squared. Then v equals v naught plus at. And then the last equation, v squared, v naught squared plus 2a times delta x. So these are three kinematic equations which you derived and used in physics 1. So now let's make a decision which kinematic equations will be the best, the easiest to use. So
The second.
the second?
Or no, maybe the third. Maybe the third one.
Yes,
The time
of course.
equation?
The major point, right? Look, guys, the first two equations, they have time dependence. We need to know, we need to have some information about time, and nothing is given about time. So we don't have any information about time, and the question is not about time, finding time. So usually it's an immediate indication that equation number 3 will be the best one, because that equation was derived out of these two for these special cases. If you don't care about time, if time is not given, so this no time equation, I usually call it like no time equation because that's the major feature of that equation. So the last one would be the best. Of course, yeah, you can use number 1 and number 2, but you will have to make one extra step in order to find what needs to be found. Right. So the best formula is the last one. Right. Okay, I thought I wouldn't be, I thought I will be able to finish it within that whiteboard. Okay. So maybe I will start using it here. V, final velocity, 0. Final velocity in this equation is 0, so let's dump it. So this is 0. Initial velocity is given, acceleration is given. Okay, acceleration is found, not given. And delta x, oh no, I need to rewrite it. All right, so v squared equals v naught squared plus 2a. And of course, what is delta x? It's x final minus x initial. And now let me start dumping terms. Velocity is 0. And of course, initial position, you see? Initial position is also 0. So this is also 0. Okay? And what needs to be found? X. So let's solve it for x. So this is our unknown. Right, so I need to move terms around. So it will be 2ax equals to minus v naught squared. And of course, from here we can solve it for x. X will be equal minus v naught squared divided by 2 times a. Okay, whenever I see minuses, it immediately sort of like it triggers thinking. Does it make sense to have minus over here? So first of all, yeah, our position cannot be negative. We are on the positive side of the x-axis, right? So x must be positive, but we're getting negative minus in front. But it should be okay because our acceleration is negative. Our object is decelerating. Of course, in our kinematic equations, we need to bring that minus. All right, so acceleration is negative. So as a result, position will be positive, as it should be. Right. Okay, so now let me rewrite it. So v naught squared divided by 2. And instead of acceleration, I will write all this mass. Right. Q eta over 2m epsilon naught. Right. Okay, so now we just need to make it look nice. 2 will be cancelled. M epsilon naught goes upstairs, minus disappears. M epsilon naught v naught squared divided by q times absolute value of the surface charge density. Right. Okay, let me check if I got what I was planning to get. Yeah. Okay, then it's a proton, but you remember charge of a proton in absolute value the same as a charge of an electron. So basically every time we assume that Q is given and M is given. You can open the book and you can find those values, right? Basically these are universal constants: charge of a proton, mass of a proton. So I'm not going to plug those I'm not going to write and plug those numbers. I will just write down the answer. So x will be equal 0.18 meters. Okay, maybe I can write charge is 1.6 times 10 to the power of minus 19 coulombs, and mass of the proton, where is my mass? Here, 1.67 times 10 to the power minus 27 kilograms. Those are universal constants, basically. Problems like this quite often I give in the first midterm exam. All right. They will be also in your homework. They will be also in the lecture. I'm not going to solve it in the lecture. You can just read. You can look at my solution. But every time, solution of this type. First, you need to find electric field, then electric force, of course, then acceleration, and then usually at the end, the question can be about finding travel time, or maybe finding the final velocity or initial velocity, right? So basically, any kinematic parameter can be here in the question, and then of course it means that you can just use kinematic equations, one of the kinematic equations. Okay, it's not pure physics 2 problem. It's sort of like a mix of physics 1 and physics 2. Actually, I would say it more like physics 1 problem, and one of the forces is an electric force. That's it.
Professor?
Yeah.
What are we using for epsilon naught?
It's a constant, that universal constant. Open the book, write 8.85 times 10 to the power of minus 12. Yeah. Again, those constants, usually when we are at school, normal semester, of course, all those constants are given in a formula sheet, right? But now, since everything is available to you, right, you can open the book, and under the front cover, here's the book, right? So right under the front cover, so all these constants. Okay, I'm not going to write it. Okay, all right. So it should be enough. Again, it's basically physics 1 problem. So, all right, if you have questions, if you have more questions, ask. Otherwise, I will start erasing this because the next problem will be lengthier and I need space.
All right.
Okay. I thought somebody wanted to ask something. Okay, cool. And basically, because of this problem, I postponed the homework because I was planning to solve this problem in the previous class, recitation class. But we ran out of time, and you need this similar problem is assigned in your homework. As your homework. So next one, 2347. Okay, again, integration. We started doing integration in our lecture, and now one more problem about integration in the recitation class. All right. And as I told you in the lecture, these are probably some of the most challenging from the point of view of calculus, right? Mathematically challenging. Okay, let me first tell you, so what we have. Okay, let's assume that you have a flexible, sort of like a rubber rod, uniformly charged. Let's say charge is given, Q, length is given, right? And then you bend it into a semicircle. And of course, it creates an electric field everywhere, but we want to find electric field at the center of the semicircle. Why that point? Because lots of symmetry, and calculations can be reasonably easy or reasonably complicated, because for any other point, calculations will be really, really crazy. All right? Okay, so let me draw the picture, and probably first I will write, so we have charged semicircle. Right, and what is given? The total charge and the total length. That's L capital, total length of that rod. Yeah. And now let me draw. Finally, I can use this device. Okay, it should be enough. Let me estimate the amount of space. Yeah, I think it should be enough. Okay, semicircle. This is the center. So let's call it point P. So we need to find the electric field at that point P. So let me write down. So we need to find E at the point P. Actually, as a vector, I'll probably write down. Okay, soon I will have to change my marker. So yeah, that's it, right? And of course, this is the center. Since we will have to find vectors, a vector, coordinate system is a must. So we must show which is the x direction, which is the y direction. Without that, yeah, it would be very strange. Right, so let me show that this is, let's say, y, and of course this will be our x-axis. Okay, so that's the situation, and now let's discussing it. Let's start discussing. Again, like in the lecture, I told you. So right now we have only one expression, one formula, which we can use. A formula for the electric field created by point charge, nothing else. So we have to use that somehow, and that is definitely not a point charge. It's a rod. Actually, now we can call it a semicircle. Right? So, and the beginning is typical, as I told you in the lecture. Let's take infinitesimally small section of this rod. Let me take, for example, it here. So that's infinitesimally small section of the rod. Of course, it has length dl, and of course there will be some amount of charge dq. And again, I will pronounce the same words like in the lecture. What does it mean infinitesimally small from the calculus point of view? It's very simple. It means that it's smaller than anything you can think of. Again, it doesn't matter how wild your imagination is. dl will be all the time, by definition, smaller. So if it's so darn small, it means that what? It means that we can treat with extremely good approximation. We can treat it as a point charge. It's the beginning for any, when you want to set up an integration. Every time you take something small and treat it as a point object. Okay, so now maybe I will write again these words. So take dl with the amount of charge dq and treat it as a point object, point charge. Okay, so that's the beginning all the time, and I've done exactly the same in the lecture. Okay, so now we can, first of all, we can draw the contribution to the net electric field at this point from that small section dl, right? Okay, maybe I will first draw a, how should I draw? Okay, so this, and so of course the electric field will be along this line. So that's the contribution dE. It's a small contribution to the net electric field at this point from that charge dq. And of course, there will be contributions from that section, that, pretty much from each section of the rod. But we took some arbitrary dl, and that's its contribution. And of course, we can write the expression for the magnitude of this electric field. Because it's a point charge, we know the expression. So of course, we can write that dE equals k times dq divided by the square of the distance from that point charge to the point P, to the point in question. Right? You see, so far steps exactly the same in the lecture. Right? So now we need to write all this in terms of what is given and a single variable of integration. Again, which variable of integration, it's difficult to tell from the very beginning, but we will just start evolving it, start diving in deeper and deeper and see what will be the best, which variable will be the best. So first, what can you say about this r small? R, it's at this distance, right? It's this, from this point to that point. And that's constant, that's the radius because it's a semicircle. Of course, radius is not given, but at some point, of course, we will express radius in terms of L, and it's simple, right? But for now, let's introduce R capital. That's not the major issue, right? So let's just use for now R capital. But again, in a few minutes, we will get rid of this R capital and use L capital. Anyway, it's constant, right? So now we know this. Now we just need to write dq in terms of what is given. dq. And now we need to recall again that slide in the lecture before I started discussing the example, integration example. You remember those linear charge density, surface charge density, volume charge density. Again, we need to recall that. And again, look, the object the object physically object is basically two-dimensional, right? Half a circle, it's a two-dimensional object. But distribution of charge is still one-dimensional. Charges are distributed over this basically line, right? Okay, not a straight line, but semicircle. Again, object is two-dimensional, but the charge distribution is linear. So we need to use linear charge density lambda. Of course, if we had a half of a disk, uniformly charged, of course, we would have to use surface charge density. But here, charge is distributed over a curved line. It's one-dimensional. So I will use lambda, linear charge density. Again, that slide from the lecture. And in order to find the amount of charge in this small section, we need to multiply it by dl. Right. And so now it looks like we introduced the variable of integration L. I don't know if it's good or not, we will see. But next step, we need to write down the expression for the linear charge density. We should be able to find it. Because total charge is given, and we know the total length over which this charge is uniformly distributed. So we just need to take total charge and divide it by the total length. It's like in that slide we were discussing, right? If you have a rod, charge Q is distributed uniformly, and if you know the length, just take the total charge divided by the total length. The same with mass density, charge density. What a big difference, right? So I can write this as Q divided by L. So it's a linear charge density. Maybe I should emphasize that this is a linear charge density. All right, N times dl. All right. Okay, so now it looks like, yeah, we wrote dq in terms of q is given, L is given, and the variable of integration L. But of course, okay, in the integral it will be dl. Now the next step, maybe like in 5-10 minutes, we will sooner or later we will realize eventually that L is not the best variable of integration, and of course dl is an integral. So let's switch, and again in maybe in 5-10 minutes you will see why. Let's switch from dl. Let's introduce the new variable of integration, and let's introduce this angle. Right, you know what, let me remove this r. First, let me show this angle. Let's introduce this angle theta. And now let me bring back that r. Right, probably I will show it here. Right. Let's introduce that angle theta. Because again, in a few minutes you will see why I'm sort of jumping ahead and said, let's at this point switch variable of integration. And so we need to connect dl with d theta. Again, let's see on the picture where d theta is. So this is dl. Of course, d theta must be an angle which supports this dl. It's at this. If I draw this line, so this will be d theta, the angle, this infinitesimal small angle d theta, which supports that arc length dl. Right? So that is theta, and that is d theta. It's a typical steps in integrations. For those of you who are familiar with integration, of course, it's banal. Of course, for those of you who are still learning, right, might be challenging. But we need to be exposed. You need to be exposed to that. Right. Okay, so now, who knows or maybe remembers how to connect this d theta and that dl? Usually at this point, students don't remember this, right? So I have to refresh. We have to refresh the how to connect them. Right. So let me first write introduce. Oops, it's a mess. Introduce d theta instead of dl. Okay, right? And now let's connect them. You remember definition of radiance. How did we introduce radiance? Okay, I will use maybe my circle.
A unit circle?
For unit circle, okay, yeah, you're moving in the right direction. You're moving in the absolutely right direction. Definition of radiance. Again, usually students don't remember that, right? All right, and I have to refresh that. If we take, or maybe I will use this. All right. No, it doesn't work. I will use by hand.
Is this like, to say 2 pi is 360 degrees, like that?
Not exactly. 2 pi 360 degrees will allow you to connect degrees and radians.
Okay.
But we need to connect r, this r, and, or actually dl and the d theta, or theta and arc length. Okay, so let's refresh. So let's assume that, okay, so we have a circle of radius r. And let's assume that we have this angle theta. Of course, you can use you can use degrees to define that define that angle, or we can use radians. What is angle? This angle in radians by definition. So of course this radius is r. This is the arc length subtended by that angle, right? So let's say L. So by definition, angle theta in radians, by definition, 3 lines, it's the ratio of that arc length divided by the radius of the circle. That's how we introduce angle in radians. By definition, 3 lines. That's why I have 3 lines. Again, okay, we can frame it. So, and now you can see, so how can we connect dl with d theta? Easily, right? So from here, of course, I can write that L equals r theta. And then, of course, since r is constant, I can write that dl equals r d theta. That's the transition. Transition.
Is it just like R is S for arc length?
No, R, it's a radius of this circle.
I'm sorry, L is arc length.
L is the arc length, of course. L is the arc length, you see? Right.
I think my calculus professor used to use an S for that.
Okay, it depends, right? Different books use different. Of course, you can use S, you can L. It's a potato, right? It's basically the same, right? Different books use different notations. So S and L, yeah, they're interchangeable, basically. Of course, R is constant because it's a circle. Okay, so that's what we need. That's what we need over here. All right? So now let me write back to our problem. Right? So now let me write dE. So now we know how to write dl in terms of theta. And so now let's put it all back to dE. So dE equals, right, so k dq is that it's a q over L. Instead of dl, we have r d theta. Instead of dl, we have r d theta, and divided by r squared. R squared, it's a capital R, right? Of course, one r can be canceled, right? And as a result, we're getting k q d theta divided by r times L. Okay. So now, of course, r is not given. L is given. So we need to get rid of r and write it in terms of L, right? Of course, we could have done it from the very beginning, but I felt like it's better to, after we went through these transitions, right? So now let's replace r. Right. So L, it's the length of semicircle. How else can we write the length of a semicircle? Pi times r. The total circumference is 2 pi r. But since we have semicircle, it's just pi r. So that's how we can connect it, right? Connect them. So it's a pi r. Let me emphasize. So it's just a semicircle. Right. Of course, so r equals L divided by pi. Right, so let's plug it, and we will have expression for the magnitude of the electric field. So we'll plug it over here. So it will be k q d theta. Of course, this pi will go upstairs immediately. Let me move pi upstairs. Oh no, let's do it step by step. Q d theta and L over pi times L. Right. So it will be k pi q d theta divided by L squared. Whew. Okay, so now that's the magnitude of this electric field, length. But again, now we need to be careful. You cannot just, of course, you need to integrate, but you cannot just grab that formula and start integrating over the whole semicircle, because this is the vector quantity. According to the calculus, what you're supposed to do at this point, you're supposed to find x component of this, or y component, and then integrate them all. Integrate them, right? So of course, at this point now you need to find E. You know what? Probably I don't have enough space over there. So of course, electric field will be integral of dEy, right? So we'll have to find electric y component of the electric field and then integrate. But let's try to skip this integration, because we have plenty of symmetry and we might be able to skip this integration. Right, so let's use symmetry to skip this integration, to skip this. What do I mean by this, using symmetry? Look, we have this section dl on the upper part of the semicircle. But at the same time, I can find symmetrically position dl on this side with the same dl, the same dq. And of course, this is going to create similar electric field, but pointing that way. And now let's look at the components, y and x components of both these fields. So y component will be here, right? X component will be here. Now, about this red, of course, the x component there, y component is here. Now look, what happens to the y components of this red and blue y components? They're the same in magnitude, but in the opposite directions. They cancel each other, brutally cancel each other. So during your integration, it doesn't matter which section you can find in the upper part. There will be a section in the lower part with the opposite y contribution. So every time y components are going to cancel each other. So this integral will be 0. Of course, I can see it graphically because of the symmetry, but if you said, but you can say, of course, I don't believe your picture, right? I don't believe your justifications, right? Okay, not a big deal. Write down this integral explicitly, and you will end up with 0 mathematically. So let's just skip it, because we can see from the picture that that integral will be 0 anyway, right? Right, so we can write that y component of the electric field eventually will be 0 anyway. So what's left? X components, of course, they don't cancel each other. X components survive, and they will give us something. So let's find x component of this electric field and integrate it. So here we cannot skip. All right. So of course, only x component survives. Right. Okay. So now let's find x component of this electric field. So we need to, let me write. So this is the x component, right? So this is dx, dex, right? You see this one, right? So this is our dE. And now we need to find this horizontal component. We introduced this angle theta. Exactly the same theta angle is over here, right? So it's this theta, you see, and here theta. Okay, now lots of red. So if we need to find this component which is opposite to the chosen angle, so this is theta, this is theta, this is theta. So we just need to multiply by sine. Okay, let me finish, guys, this problem, couple of minutes. So we need to multiply it by sine of angle theta. So you see now that's why we moved at this point from L to theta, because I knew from the very beginning that this sine theta will pop up. So that's the reason why I moved from L to theta. Okay, so now basically we just need to start integrating. So let me write this dx. Instead of dE, I will write this. So it will be integral of out of k pi q L squared sine theta d theta. So I just plug dE instead of this dE and multiply by sine, and of course integration. Limits of integration. You start from here because you see we measure angle theta from the vertical, from the positive y direction. So when you are here, angle theta is 0. So the lower limit is 0. All right. And then when you get to the lower part, to this part, to the end of the rod, you are at this point and the angle is pi. So 0 from 0 to pi. So that's the integral. So all these are constants. So we can take them outside, and then we have integral of sine. Right. So it will be k pi q over L squared and integral of sine theta d theta from 0 to pi. This is a trivial integral. Integral of sine is minus cosine. So it's a k pi theta over L squared. This problem is actually in your homework also. So you'll have to just repeat it by yourself at home. And minus cosine theta with limits from 0 to pi, minus cosine theta. Okay, I'm running out of space here. All right, so it will be minus k pi q over L squared. And cosine of pi, upper limit cosine of pi is minus 1. And then minus cosine of 0 is 1. So as a result, you're getting the minuses will disappear. And we're getting the answer and the end of the class. Right, so 2k pi q over L squared. So that's the answer.